Good afternoon, everybody. My name is Ahmed Mahmoud. I'm the Chief Operating Officer and member of the Board of Directors at Ally Power. And today I'll be co-presenting alongside Shashank Kara on the simulation of Ally Power's clean hydrogen production process using virtual reactors, new vapor, liquid, and solid capabilities. So a brief background about Ally Power. We're a startup founded in 2019 by Walt Joseph Alfred, who's the inventor of the hydrogen and electric refueling station. And we're one of the only clean hydrogen production processes that produces electricity. And we do that via a chemical reaction process between a liquid reactant and a solid material feed. And when these two materials interact with each other, they produce carbon-free, NOx-free hydrogen, a liquid byproduct that's widely used in the wastewater treatment industry as a coagulant and the cement industry as an additive. And also we generate quite a bit of heat, which we recover to produce electricity. And at Ally Power, we're a hydrogen company, so we're focusing on the two main industries in hydrogen, the industrial sector and the mobility sector. And so at Ally Power, we are focusing on creating circular economies while decarbonizing those hard-to-abate industries, such as concrete, cement, steel, and aluminum manufacturing. And I joined Ally Power in March of 2023, and at that time it was about 4 or 5 of us, and about 19 months later, we're 12 strong, and we have 8 core team members with different backgrounds: mechanical, chemical engineering, manufacturing, operations, risk, sustainable finance, and business development. And some of you have probably met Zarab Chowdhury. He's one of our board members. He's with me here today. So, Zarab, thank you for joining. And so, when we first met with CPFD about 6 months ago, we didn't have an engineering package. So we had a reactor drawn on a piece of paper with some rough dimensions, and I sent it over to Sam and Rosemary and said, hey, that's fine, we can work on it. So we sent them over some geometries, inlets, outlets, boundary conditions, and material properties. We also sent them a multi-phase reaction that consists of a liquid reactant plus a solid material feed that produces hydrogen and a liquid byproduct. And when we were working with the CPFD team, we were strategizing on how we want to visualize our simulation. And one of the most important aspects was, of course, showcasing the hydrogen bubbles being produced. So, Shashank, do you want to touch on that aspect and the equilibrium between phases and some of the new modeling features that you guys applied in our simulation?
Yep. No, thanks so much, Ahmed. So I guess this has been quite an interesting application for us and novel in many ways because it's allowed us to use many of the new features we have developed over the last few years. To start off with, as the reaction down there starts, we have multiple liquid species here. So you have a liquid reactant which is reacting with water. So that is a new feature we have added in the past few years. Obviously, these two liquids are reacting along with the solid reactant. So that is the second feature we've been using in this simulation. Then we also have compressible bubbles. Obviously, this is an incompressible flow simulation, but inside of this incompressible flow simulation, we can have compressible bubbles which change shapes based on the pressure in each computational cell, thereby changing the basically how much volume is displaced and so on, right? And importantly, we also have the gas absorption model turned on in here. So the idea is this hydrogen byproduct that we produce, it can either exist, it is either dissolved in the liquid, or it can come out as a gas and then forms a bubble, right? And the equilibrium is kind of based on Henry's constant, right? So the concentration of the gas dissolved in the liquid versus the partial pressure out in the gaseous phase. So based on that, that's also sort of included in the modeling effort. And more importantly, these bubbles can come together, they can become bigger, and they can break up as well. So all these features, this is a sort of an application where we have had to include all these new features, relatively developed in the last few years. With that, I'll turn over to Ahmed again.
Thank you, Shashank. Before I get into the next slide, we'll just touch base on the CAD model here. Very simple, rudimentary design. Basically a pressure vessel reactor, 2 inlets, one for the solid material feed on the right-hand side, one for the liquid reactant on the left-hand side. And then we also have 2 outlets, one for the hydrogen on the top and one for the liquid byproduct on the bottom. So all these simulations that you're going to see, I have to give credit to Shashank. He worked with us the past 3 months. So all credit to him when it comes to the simulations. Thank you, Shashank. So when we first got the baseline simulation, we were really ecstatic because we finally were able to demonstrate how our products formed, how the hydrogen was produced, and how the heat was generated. But we also identified challenges in our design. So as you see here, in the right-hand side, that's where the solid material feed is coming in. It's skewed towards one side of the reactor. So creates 2 problems for us. The most evident one, obviously, you see is a heat spot. But also, you don't see it that much, but it creates a channeling of that solid material feed towards the bottom of the reactor. So those are 2 things that we don't want in our design. So we went internally and we discussed with CPFD, and the goal is to have an equal distribution of raw materials into the reactor to allow for a more equal reaction inside our system. So basically just added more inlets. So to be exact, we had 4 inlets for the solid material feed and 4 inlets for the liquid reactant. And we separated them by 90 degrees around the circumference just to get that equal distribution of the raw materials. And so this simulation shows the reactants mixing with each other. The green is the mass fraction of the liquid, the liquid reactant. And I'll focus here on the baseline first, and we'll get into the improved design. But as you see here, skewed towards one side of the reactor, where the improved design showcases a more equal distribution of the raw materials, thus creating an equal reaction throughout our system. So let it play here one more time so you guys can see. Great. Let me go back because I want to talk about one of my favorite features here at CPFD is that you can utilize unique views to and format your messaging for the certain application. So, Shashank, do you want to touch on that a little bit?
Absolutely. I guess, part of the role was, as we know with these simulation software, right, the ability to sort of view inside the reactor that you wouldn't necessarily be able to see in an actual system that's built. So with these, changes that the new design went through, obviously, cutting through slices along where you're feeding the particles versus where you're getting in the reactants, and then also having a radial view of the same thing happening, right? So you have these aluminum particles, for example, in the improved design coming from all 4 different directions. And then when you sort of look from a radial view, you see how the reactants are being consumed. So essentially, as we've seen through several presentations throughout the day, right? Once you set up the model inside the software, literally the kind of data that you can get, whether it's qualitative or quantitative, is pretty much limitless. And sort of for this application, that feature comes in pretty nicely.
Thank you, Shashank. And so, even more evident, and this is my favorite animation here, it showcases the heat generation. You see here the heat spot being formed in the baseline design, again, because of the reaction skewed towards one side of the reactor. But in our improved design, a more equal heat distribution throughout our system. And then on the left-hand side here, you see the hydrogen bubbles being formed. In the beginning of the simulation, you see that it's a little bit different, but after the hydrogen is formed, fills up the reactor pretty quickly. So no big difference. But in the liquid reactant, this is where you can also see a clear difference between the baseline and the improved design. Again, in the baseline, skew towards the right side, where in the improved design, you see a more equal concentration of the liquid byproduct that's generated. So it's important to note that these models are helping us conceptualize our chemical reaction at an industrial scale. And that's valuable to us because we're the first and only ones to work on the commercialization of this chemical reaction. And so this has increased our optics for both our internal and external engineers to help us optimize our design and process engineering. And so in the past 6 months, this has helped us decrease our commercialization timeline by 50%. And in the beginning, we thought we'd save around $200,000, but once we started doing light items and got our final quote, we actually saved $517,000 from going out there and building that baseline model. And if we didn't have Barracuda Virtual Reactor, that's would have lost out on money and would have failed epically, unfortunately. But in the medium term, we plan on proving out all our designs for our minimum viable product, our pilot, and our commercial proof of concept in Barracuda Virtual Reactor. And in the long term, we want to work with CPFD like how they're working with Shell or Cemex, and be able to optimize and develop new systems to deploy in Allied Power's hydrogen and electric refueling stations. So the final animation here is a higher resolution of our reactor and our reaction, and towards the beginning of the actual reaction. So the other simulations were a more stable rate reaction, but this is towards the beginning. And so you see here more clearly the equal distribution of raw materials into the reactor, allowing for more equal generation of our liquid byproduct and the hydrogen as well. So that being said, I want to give a special thanks to CPFD. Peter, thank you so much for your support. Shashank, also thank you for your work. Sam, Rosemary, and the rest of the CPFD team, thank you. Appreciate it.